Hello, welcome back after spring break. Bless you. Did anybody do anything exciting? You worked? Good, that's the right answer. You worked by yourself or you had your agents work for you?
Empirical.
Okay,
Yeah.
good.
One agent.
Did you see the code review agent that came out yesterday? Um, Claude has a code review agent now that costs about $20 a pull request in tokens. It doesn't count towards your subscription. You pay per token. And in their experiments, it would be about $20 of worth of tokens per PR.
I saw something, I don't know if this is real or not, because I think it's just people doing their best guess based on usage and stuff like that, but I saw something that like, whatever like the pro tier is, like, it's like $200 a month or something for, I think, Claude. And they went through and tried to analyze like how much Anthropic is paying for those users.
Yeah.
And it's like between $4 and $5 grand a month.
Yes, it's heavily subsidized. We know this. Yeah. Yeah, if you were to pay how much it costs them, you'd be ruined.
Price pay.
Not at that cost, I can imagine.
They have to pay a person to do stuff.
Oh, yeah, right.
Yeah.
Sorry, I misunderstood. I thought you would be willing to pay 5 grand a month or something for tokens. Any gossip?
Yes.
Everybody's wearing black. Is there something happening?
I think it's because we're at war now, so
Yeah.
we had to.
All right. Today I want to talk about the logic of causal inference, and we're starting to talk about experiments as a method for testing for causal or establishing causal relationships. This we'll be basically talking about causal inference in one form or another, more or less for the remainder of the semester. So this part today especially is super relevant. So yeah, please engage. And I brought candy to stimulate you. Okay. And throw at you if you would like, or you can help yourselves. You know, we throw candy at the undergrads when they participate in class, when they say something.
I've seen the production recordings and I've seen.
Yeah. That's one, yeah. I think I don't know where it started. I stole this idea from maybe Michael Hilton. Okay, you could look at these book chapters here for more details on what I'm going to talk about. Okay, so let's start with this idea of causal relationships, which is kind of important. Hello. So here's a mouthful for, first of all, what these things mean. We talk about cause and effect in a causal relationship, but what does it mean for something to be a cause? So here's a mouthful. A cause is an I-ness condition, meaning an insufficient but non-redundant part of an unnecessary but sufficient condition. Now say that 3 times really quickly. I'm kidding. Right? So let's parse this for a second. Think of the example of a match, lighting a match to start the forest fire. Okay? Is this match the cause of the forest fire? Okay? So here's how we think about this. Fires can start for all kinds of other reasons that have nothing to do with matches. For example, I don't know, lightning strike, or I don't know, electrical transformer or something going bad or whatever. Okay? So the match is not a necessary condition for this effect to exist, to be present. It's also not a sufficient condition because lit matches don't always start a forest fire. For example, if the ground is wet, you probably won't get anywhere. Okay? So it's neither necessary nor sufficient for this purpose. But it's part of this bigger constellation of conditions without which it would not be possible to start a fire. Right? So, it needs oxygen, it needs the leaves to be dry, etc. And also it needs to add something unique to this, right? So, if the fire is already starting by itself, when these other conditions are present, the match doesn't add anything unique. So for it to be a cause of the forest fire, it needs to add something unique to this mix. Okay. So then the effect is to think about the effect, we think about the counterfactual. But has anybody watched this series? It's called The Man in the High Castle. I think it used to be on Amazon Prime. It's a really good fiction series about what would have happened to the US if they had lost the Second World War instead of winning it. So I give this as an example of counterfactual reasoning, right? So counterfactual reasoning, what would have happened to whatever the subjects of your study had the cause not been present? What would have happened to the forest had the lit match not been present? Okay, so we observe what happens to our study subjects when we administer some intervention or a treatment. That's observable. But we cannot observe fundamentally, right, by construction, we cannot observe what would have happened to those same subjects in the same conditions at the same time had they not received the treatment. This is fundamentally unobservable. Right? You can never observe the counterfactual. So the effect is the difference between these two things. The effect is the difference between what actually happened and this counterfactual, what would have happened, right? If everything else had been the same except for your cause. Okay? And this is unobservable. Right? Do you see why that's the case? Because we can just be in two parallel universes all at the same time in the same condition. Like anything else would alter the setup, it would not be the same. It's just fundamentally unobservable. So like all of this, causal inference or reasoning is about approximating, about finding a good source of counterfactual evidence, getting as close as you possibly can. But you can never actually observe or measure the actual thing. It's not an actual thing. It does not actually exist. Okay? That makes sense? This is a really key part of the whole story. So I want this to be super clear. Right? So when we talk about the effect, we talk about the difference between these two things, but one of the two things is fundamentally unobservable. Okay? All right. Right, which is why we have to approximate it or infer it. So we, right, so then the trick is, or the challenge is, how do you approximate it? How do you infer it? How do you get as close as you can to a good estimate of the counterfactual? So, okay, so we may have talked about this, I don't remember. If we want to establish a causal relationship between two things, say a cause and an effect of it, what properties must we establish for there to be a causal relationship between these two things? What properties must hold for the cause and the effect for there to be a causal relationship between them? Marco.
So let's say the cause is A and the effect is B. So when you apply A, then B either happens, so like binary, like 0, 1, or happens more often.
Okay, good. So this is one. There has to be some observable association between the presence of the cause and the effect. Right? There has to be some association. If you apply the cause and nothing happens to the effect, if there is no effect, that's maybe unlikely for that to have been the cause. So yes, there has to be this measurable, observable relationship between the two things. Whatever the nature of the relationship is, it doesn't really matter, right? The shape of it, but it has to be present. Okay, that's one. What else?
Uh,
Cause being a necessary condition. However, the cause must happen before the effect.
Yes, that's the second key element, right? The cause must precede the effect. It cannot happen afterwards. But otherwise, it could not have been, I mean, in this, whatever system of physics laws, it could not have been the cause for it. That's the second one. Okay. So now going back to our discussion, I don't know, a few minutes ago of the match in the forest and whatnot. What's the third one? Let's see, someone else. Marco is on a roll. We'll give you some candy. Do you like Sour Patch or Nerds? Sour Patch. Oh, that was a shameful. Do you like Sour Patch or Nerds or something else? I also have candy corn and Swedish fish. You tell me.
No,
Say again?
no.
Nerds. Nerds I have. Oh, that's pretty good. What's the third one? Rob,
Not happened anyway.
would not have
The
happened.
effect would not just happened anyway. Maybe the same as the last one.
Yes. Yes, so that I agree. This is the third one. What's another way of saying the third one? No, Marco is banned. See, this one's candy. Yeah, please.
Happened by something else.
That's it. That's another way of saying the same thing. What did you have?
I was saying basically, like the effect doesn't exist without it.
That was the association bit we started with. There's some relationship between the two that's observable. Would you like Sour Patch or Nerds or which one? Nerd? That's on you. I was close enough. Would you like some candy?
No.
All right. Okay, so I want you to really internalize this slide, basically, because everything from now on will be thinking about these three things for the rest of the semester, more or less. Okay, so this temporal order has to be there, right? The cause must come before the effect. There has to be some measurable relationship between them, whatever its shape. And this is so like the first two, right? The first two are easy. Right, time easy, measurable relationship easy. Third one is the moneymaker. But there has to be no plausible alternative explanation for the same effect. Good luck with that. Right? Because how can you know? So this is why this is super hard to do in practice. And why, why experiments are a great way to establish the presence of a causal relationship, because experiments more or less give you the third one as well. The first two are easy. You can always get the first two. The third one is the one that's hard. So why am I saying this? So experiments, by experiments, I mean randomized experiments or true experiments or randomized control experiments. So the idea here is to be able to manipulate the treatment. Okay, so long as you're able to do this, you can randomly assign subjects, participants, to conditions, for example, with and without the treatment. It's what happens with, I don't know, drugs or vaccines or whatever. Okay, so this gives you two groups, right? Each group is participating in the experiment in a different condition. One, for example, receives a placebo, the other one receives the actual treatment. Critically, they don't know what they're getting. Okay. And you're then measuring or whatever, observing the outcomes, right? So why is this a good design? Why is this the gold standard, by the way, for science in terms of research design? Why is this the gold standard design? Why is this so good?
This, you don't have to worry about all the variables you don't know about, because the only thing that's different with the variables is what you measure.
That's the point. Yes, Marco.
I was just gonna say, it satisfies the three things that we just said really, really nicely.
Yeah, especially right. So it satisfies the third one very naturally and nicely because on average, if the two groups are large enough, things that are different between your subjects will, on average, be similar between the two groups. Right? You will have, on average, as many tall people as short people in both groups. You'll have on average as many people who like Love is Blind and who hate Love is Blind, whatever, right? So yeah, there's a caveat there, right? If the groups are large enough, and if people don't drop out of the study and so forth. So there's a few, footnotes, but by and large, the magic of random assignment ensures that the two groups are indistinguishable, hopefully in all aspects, except receiving the actual treatment. So it very naturally solves this third problem that is super hard to solve, right? If there's still a difference in outcomes between these two groups, it's very unlikely that it's due to anything else but the thing you manipulated yourself, because everything else you expect can be similar between the two groups. Okay? So hopefully this is not surprising. Hopefully you've seen, you've seen this. You've thought about experiments before, and you've seen this before. So today we're going to talk a bit more about designing the actual design of experiments, but really this logic of what it takes to establish a causal relationship will follow and haunt us more or less forever now. And all of the things we do later, observational studies, etc., various forms of causal inference and observational data, so not actual experiments, all of those things, every time we do something like this, we will think back at the three ingredients and think back at how close does this get to excluding plausible alternative explanations. Okay? So this is going to be the most important thing you learn today, probably, is the sort of this logic of causal relationships. In this class, I don't want to speak for other things you're doing today. Okay. Just as an aside, these are two terms that are often confused, so I will bring them up now. Have you heard of mediators and moderators? These familiar? So, okay, so let's say we have some independent variable x that we expect causes a dependent variable y. So in that sense, y depends on x, right? If x causes it. So a mediator is another path in this causal relationship that could get from x to y, right? So m here is a mediator if you can get from x to y through m. So in other words, the effect of x on y may be some of it may be direct, or none of it may be direct, right? But some of it goes through this mediator m. So here's a concrete example to make this hopefully more intuitive. So let's say socioeconomic status of the family or something like this causes reading ability differences in children. right? So, children in families with higher socioeconomic status can read better, because, I don't know, they have more books at home or something like that. Okay? But a mediator here is maybe the parent's education level, right? Because probably parents that came from higher socioeconomic status families obtained, had more access to education when they were growing up, obtained higher degrees on average. They maybe value education more or whatever, and in turn, that it impacts how well their kids are able to read because they push their kids to read more than other parents. Okay? So the effect of socioeconomic status on child reading ability here is mediated, for example, by the parent's education level. Right? There's a plausible alternative explanation for differences in reading ability in children, right, other than socioeconomic status, or it's like socioeconomic status through the parent's education level. Right? So if you want to test, for example, the size of the effect of socioeconomic status on children's reading ability, you have to close this other path somehow. See what I mean? I'm seeing some maybe confused faces. So all questions are on the table. Ask anything. Okay. All right. So that was a mediator. A moderator is a variable z here that depending on its value changes the strength or the magnitude of this causal relationship between x and y. So I'll give you an example. Let's say work experience causes your income, your salary, right? The more senior you are, meaning the more work experience you have, the higher your salary will be. Okay. But turns out gender moderates this relationship. Right? For example, in this country, women make however many cents on the dollar compared to men. Does anybody know what's the latest number?
84.
84? Okay.
It says 81.
All right. So, so depending on gender, right? The strength of the relationship, the magnitude of the relationship between work experience and salary will vary. But gender is not a mediator here. Work experience does not cause gender, right? So this is like qualitatively, hopefully you notice, very different from the previous example. Right? Socioeconomic status causes the parents' education level to a large extent, presumably, right? Because their families have more, I don't know, they can afford more education, they can afford to send their kids to school, etc. Work experience here does not cause gender, clearly. Okay, so mediators versus moderators. We'll talk about these a lot later as well. Okay. Very confusing terms. Maybe I should do a quiz next time or something. Okay, and you've heard this, correlation is not causation thing, I'm sure many times. I won't insist on this. Yeah. So, for example, right, right. So why is correlation not causation? Because it misses two of the three elements. Correlation is there is a measurable association relationship between the two variables. But for example, if we don't know which one came first, well, we can be quite sure. And if we can't exclude plausible alternative explanations, then we also can be quite sure. So that's really the idea here. It is one of the three ingredients we need, but it's not enough. Okay. Yeah, and you've seen, sort of memes like these, I'm sure, many times. Nick Cage, favorite actor of mine. Apparently, the number of movies he appears in correlates very highly with how many people drown by falling into a pool. And you've seen many such examples. Computer science doctorates awarded in the US versus total revenue generated by arcades. So arguably, these things are not related. These are just coincidences. Okay, so back to experiments. What are some, so we talked about experiments, where sort of you're able to manipulate the treatment, you assign participants to different conditions and observe differences in outcomes. Right? What are some disadvantages of this setup? We talked about a great advantage, which is the gold standard for establishing causal relationships. What are some disadvantages? Andrew.
Smaller sample sizes.
Yeah. Would you like some candy? Any preference?
No.
That's one. So, experiments you can't as easily scale. Some of the online experiments like A/B tests that, companies do with their software products, those scale more easily. But largely, lab-like experiments with human subjects do not scale very easily. What else? Rob?
You can't blind all of this. You can't make every study blind.
Yes, so there could be some contamination there. Yes, people know they're being studied, I guess, is what you're.
Well, or you can't make it a blind placebo, but this comes up in my exercise all the time. You can't make someone run fast and not run fast and not know who's doing which.
Yes, there's that. Thank you, Marco.
Something that comes to mind with the Nicholas Cage example is there's too many variables to control for.
The point is, it doesn't matter. You randomly assign people to conditions. So it's the magic of random assignment that controls for the too many variables. So that's a plus, I would argue, maybe not a minus. Right?
Like a dog play might not help you identify the true cause or like true mediators. Like if you go back to the Scurvy example where people are giving like lemon, I mean that establishes causal relationship, but that's not the theory.
Yes, so that is a really important disadvantage, I guess, of all of these. Ultimately, it's not unique to experiments, but it's shared by experiments. They're good at establishing that there is a causal relationship, but not at describing the mechanism behind it, right? And we talked about this before with scurvy. We don't know why there's a causal relationship. Yes, we can observe there is one. Yes, we can be confident there is one. It's a great design for that. But we don't know why it's there. Right? We don't know what the mechanism is. Right? We have to do more work to figure that out. It does not come as an outcome of doing an experiment. This understanding of the mechanism, the theory, if you will. But maybe we don't need to know. Maybe it's enough to know that there's a causal relationship, right? If I am a tech company and I want to make more money selling ads, I don't need to know why people like to click on green buttons more than they like to click on blue buttons. Maybe, right? I don't care. I just want them to click more on ads. So whatever the mechanism is, sometimes I just don't care. Being able to predict that they will click more on green buttons is good enough for some practical purposes. But generally, right, for, I don't know, like scientific inquiry and understanding reasons, you may want to understand also what the mechanism is. And that's not enough to get from an experiment. What else? There's maybe one more.
Maybe there could be some ethical issues that will prevent us from running experiments from the first place.
Yeah, sometimes you just can't do them. Yeah, you can't. randomly assign people to do something that is likely harmful, for example. Yes, so there's that. Nobody has yet mentioned my favorite.
Like, I don't know, might not qualify as an experiment altogether, but like, what if you're testing a tool, and in order to test the tool, you need like a certain population. So by definition, the people who you're sampling for the control group and the treatment group are different.
Yeah, so I think this is as close to my favorite as we'll get. Namely, they will, I think, necessarily almost always be relatively artificial. They have low external validity, right? So, however well you design them and however well you sample participants, um, because they're small scale and because they're relatively short term and relatively, small, simple tasks, whatever. Um, it's always unclear what will happen in the wild. This is my favorite one. I've been doing, I don't know, studies of things in the wild precisely because of this reason. I just like to observe kind of what happens in reality in the wild, more so than in the lab in a controlled setting. But all of these that you've mentioned are valid disadvantages of doing experiments. Yeah, we talked about the button and selling ads. Yes. And with all of these limitations, they're still the gold standard because there's simply no better way to exclude plausible alternative explanations for something than the magic of random assignment. So yeah, for all their limitations, they're still really, really great at establishing causal relationships. Okay, so let's talk a bit about the vocabulary of experiments. So when we say experiment, we mean, for example, so a study in which any intervention is deliberately introduced to observe its effects. So, like you introducing a new tool or something to observe how people get better at some task could technically be considered an experiment. We usually refer to a randomized experiment when the assignment to conditions is random. So that's the gold standard is a randomized experiment, not necessarily an experiment, because of all the reasons we just discussed. There's also a quasi-experiment. This is a technical term. So a quasi-experiment is an experiment in which units are not assigned to conditions randomly. They are assigned through whatever other mechanism. Maybe they're self-assigned, maybe whatever else. They're assigned by you, but just not randomly. Right? So you can see hopefully how this is necessarily weaker, right? Because you cannot be as confident as when you have random assignment that you've excluded plausible alternative explanations, right? So of course you would prefer to do a randomized experiment if you can, but sometimes you cannot. So you will just do a quasi-experiment because that's what's available. A quasi-experiment will be better than no experiment. So you'll do that instead. There's also this term natural experiment. Have you heard this before? So this is basically, it's not the research team that manipulates the intervention, the treatment, but something that occurred naturally or in the wild. For example, yeah, think pandemic or something when we had to go work from home or whatever else like that. That's a natural experiment, right? It's maybe not the research team that introduced the pandemic, I guess depending on which conspiracy theory you believe in, but rather maybe it just happened as a natural phenomenon and that created an experiment. Okay, and finally, we talk about correlational studies or observational studies. When we simply observe and maybe measure the size and direction of relationships between variables without actually introducing any intervention deliberately. We, I mean the research team. So it could be that somebody else introduced the intervention deliberately. For example, we studied the adoption of tools in open source teams. That's an intervention, but we were not the ones that introduced it. So that's an observational study. Okay? Okay. Yeah, we talked about randomized experiments. Yes, so are there multiple groups or conditions involved? So all of these are design studies. Are there multiple conditions or groups involved? If yes, is there randomization involved in the assignment? If yes, then you're doing a true experiment. If no, then you're doing a quasi-experiment. Otherwise, you're not doing an experiment at all. This is another way to think about these. Okay, so now let's talk about some designs used with random assignment. So here, a basic treatment versus control, X is treatment, C is control, shows that there was random assignment R in both of these conditions. Okay? Then there was a treatment in one of the groups, that's the X. And then we are observing or measuring outcomes. Those are the O's in both groups. Okay? What can we and cannot we claim based on this design? So we're studying the effect of the treatment X here, is the point. Randomly assigned participants to either X or nothing, and then we measure outcomes. I didn't expect this is going to be a gotcha question, so it's good that we're pausing.
So just to maybe I don't understand. So R represents the participant.
Yeah. R represents random assignment to conditions. So both conditions were randomly assigned, meaning people, I don't know, half the people were randomly assigned to X, half the people were randomly assigned to nothing.
And O is the different outcome.
And O is you're measuring whatever you're measuring as an outcome in both groups to then compare the difference to then claim something about the effect of X.
So then if you're hypothesizing that applying X causes a change in O or something, then the first step would be to say, hey, not applying X doesn't cause a change in O.
Yes. So what's missing? What don't we know? So another way of saying what Marcus said is that if there's a measurable difference in outcomes between the two groups, we don't know if it's because of X or if it's because of receiving any treatment. It could be that Y would have done the same. Right? It's just the act of being treated that could have caused a difference in outcomes or a combination of both. Right? So this design by itself cannot distinguish between X as the cause of the effect versus just being treated with something as the cause of the effect. Okay? So that's the one critical thing that's missing. So think back at, plausible alternative explanations and so forth. Right? We're missing that part. We just don't know. It could be X, but it could also just be any X, not the particular X. Right? So that's not great in terms of a design, right? We would ideally like to do better. So one Yes, so I explained this. We talked about that. So here's an alternative. Right, so one thing you could do is to have treatment versus placebo. Okay, so you're still giving a treatment. So that this would be XA versus XB, right? Active treatment versus placebo treatment, right? Or you could have all three, right? You could have active treatment versus placebo treatment versus no treatment to isolate all of these effects, right? Because maybe receiving anything does something, right? And then separately, the active ingredient in one of the two treatment conditions, right, probably does more than the placebo. Okay? But the point is, the first one by itself does not quite get you there. It's not enough. Yeah, so yeah, the middle one, one disadvantage is there on the slide. If there is no difference, then you don't know if the two treatments were equally effective, which is why there's no difference, or equally ineffective, which is why the third design is better because it allows you to differentiate between those two. Okay, make sense? Okay. Yes, all right. So then, whatever design you pick, all of these still have another common limitation, namely that there is no pre-test, right? We test the subjects post-treatment. That's the O. We test for outcomes. We don't test the subjects going into the experiment pre-treatment. That's called a pre-test. Okay. So that could be a problem if there's attrition, which there often is. Attrition means people drop out during the experiment. Okay? They may drop out at different rates. So unless you can reason about the people that have dropped out being similar to the people that remained in the experiment, you can't quite reason about the effect at the end, because you don't know if the effect is there or not there, because of the treatment or because of the difference now that you've introduced in the two samples because of attrition. Like some people just dropped out. Maybe the best performers on whatever task dropped out because they got bored of your experiment, right? And one of the conditions. You see what I'm saying? So all of these suffer from that possible limitation. So then, how do you fix this? Well, you pre-test, right? You test people before going into the treatment at the beginning of the experiment. This allows you to reason about, for example, among other things, how well randomization worked. How indistinguishable are the groups on whatever you care about, right? They should be indistinguishable, right? Going into on their pretest scores, whatever that means, they should be indistinguishable between the groups, right? Because you have yet to treat them, you have yet to administer the intervention, right? And similarly, you can see if the ones that dropped out were somehow fundamentally different based on these pretest scores from the ones that remained, if that's the case, right? So you can reason about how your samples are still representative even after attrition. And of course, you can always do this, or maybe you don't always want to pretest because if you pretest, you might give away the purpose of the experiment, and that's maybe undesirable. Sometimes you can do that. So you can always do this, but that's one common solution to this problem. Okay, so then Then, we go into these pre-test, post-test designs, right? So you test before treatment and you test after treatment, with or without different treatments like this. Then we could talk about factorial designs. So this is when you have multiple treatments or multiple interventions. Okay. A and B, you have two types of treatments here, two types of interventions. So the question becomes, how do you administer the combinations of these, right? So some people get A first. Wait, what am I saying here? Oh no, so there's two possible values for each of these things, A and B, right? So one group gets nothing, neither A nor B. That would be, say, A1, B1. One group gets no A but gets only B. One group gets only A but no B, and then one group gets both. Right? So you need sort of the all combinations of these things as different conditions. Right? If you're testing for multiple things, you need to have a factorial design. So you can hopefully see how this is getting complicated pretty quickly. Right? Because you will need to have exponentially more participants if you keep doing this. Okay, then we could talk about longitudinal designs. So this is when you can, observe participants over time longitudinally. Maybe there's a bunch of pre-testing that happens before treatment. There's a bunch of post-testing that happens afterwards. Or we could talk about crossover designs. So this is where they receive treatment at different times in different orders, kind of like the factorial design, with testing in between, before, after, and during. Okay, this is just sort of one set of common designs that you may encounter for experiments. Okay, so now let's see. Another way to think about this, maybe you've heard these terms, within subjects versus between subjects. Yes, no? Some knows, mostly knows. Okay, so let's talk about it. Or yeah, within group or between group. So between group means, or between subjects means people do one thing and one thing only. And so if you have two conditions that you want to test for, right? Each participant is tested only in one of the conditions. So that means you need more participants to be able to test all these conditions between subjects or between group. Within subjects design is you test the same participants on different conditions, right? So I give you, two kinds of things to do. Okay? So I need fewer participants this way because I can, get more out of each of you, right? But then there are other problems. So let's talk about what those problems are. Oh yeah, so here's an example. Between subject design, let's say I have three types of keyboards, and I want to test how fast people can type using different keyboards. There's the traditional QWERTY keyboard. There's a Dvorak keyboard, which is the one on the bottom left there. And then there's an alphabetic keyboard, which is the one on the bottom right, in which the keys are just sorted alphabetically. Okay? So between group design or between subjects design of an experiment to test for the effect of using different type of keyboard on, say, typing speed, right, would assign different groups of people to exactly one of these conditions randomly. Okay? and then it would compare outcomes. Right? So if, for example, I give them all a task of typing a 500-word document. Right? Each participant types exactly one document using exactly one type of keyboard, but which keyboard they get is randomly assigned. Okay? So this is great, right? If because of random assignment, I can expect the groups to be comparable. So then if there are differences in typing speed, I can attribute them to the actual keyboard that they used. Okay. But also, I need a lot of participants to do this, right? Because alternatively, I could just have, uh, 3 times as few participants, and I just give them all, different documents to type using all of the keyboards, right? I don't, why do I need 3 times as many participants? I could just get away with fewer, right? I just test them on multiple keyboards, right? Instead of testing each on only one keyboard, right? So now here, each participant types 3 documents, say, right? Using each one of these keyboards to see, when they are faster. So that's great for, like how many participants I need, experiment size. Why might I not like this though?
You're introducing too many variables, right? Like the same participant doing the same task.
Is a good thing that that isolates the effect of the participant.
Yeah, but there is like the second time the same participant is doing a task, they're already familiar with it.
And I think it's like systemic errors. So you try to shuffle around and account for that.
So we call these order effects. But there's two things here. So let's talk about them separately. The first part is, so you mentioned, it's the same people doing, something. So there could be individual level variables that would explain their outcomes. That is a risk here, right? Because the groups will be relatively small, so you'll end up with a few expert typists or something in one of the groups, that will skew your results significantly, right? Because of these individual level differences, that will make one of the groups here, because of 1 or 2 participants, much more productive or effective, right, than the others.
Yeah.
Not so much the keyboard, but rather these individual level traits.
Yeah.
That's not a risk here, right? Because however expert you are at typing, that expertise will presumably be shared right across these 3 conditions. So that's an advantage of these within subject designs. But the big disadvantage, to Shrek's point, is all of these order effects. So let's talk more about that. Okay. Do you see the point here? About order effects? All right, so let's, yeah. So there's 2 types of order effects. It could be learning. So that means I learned from the first condition and I do better at the second one, not because the keyboard was better, but because I got better at typing on anything. Okay. So learning effects would favor conditions completed towards the end of the experiment over the ones at the beginning of the experiment. Or there could be fatigue effects, which is another type of order effect that's in the opposite direction, right? I'm most attentive at the beginning of class, and as we get closer to the end, I'm less and less attentive, right? Same for the experiment. I'm most engaged the first time I do the task, but I'm increasingly less engaged and yawning, right, as the experiment is progressing, right? So these are 2 types of order effects that could screw things up here considerably. So the clear winner is the between groups or between subjects design, because everybody does just one thing, right? So there, by construction, by definition, there's no opportunity to to learn from one condition to the next. There's only one condition. Okay? It also takes less time to complete, right? So it's just shorter. So also good. More likely to be able to recruit participants if you tell them your study will take half an hour, than if you tell them your study will take an hour and a half if you need to test them on 3 conditions that are half hour each, right? So just easier to convince people to participate, and no order effects here, no learning effects. But like obviously you need a lot more participants to do this, so that's the trade-off. Right, we talked about these individual differences that could obscure the effect maybe if they're overrepresented in one of the groups in this between subjects design. So the winner there is the within subjects design, right? You're able to isolate by design these individual level differences that could explain the differences in outcomes. It's also better because it allows you a smaller sample size. You can do with fewer participants. Right? Because you're comparing the performance of the same participants in different conditions. It's not always possible to do a within subjects design, even if you might prefer it though. For example, if you're testing a hypothesis like this one, that there's no difference in the time required to implement a web server in Python between novice developers and experienced developers, this is fundamentally not testable with a within subjects design, because you cannot turn novices into experts between conditions as part of the same experiment, and vice versa. Right? So there's a class of things that you may want to test that is fundamentally impossible to test with a within subjects design, even if you want to. Right? So in that case, then there's no choice. Right? But otherwise, they have a number of advantages. Okay, and I think we talked about these. Yeah, harder to get statistically significant effects, meaning at the same sample size. So you need 3 times or whatever as many participants to have the same statistical power. Okay, so then we didn't really talk about order effects. We talked about them being a problem, but we didn't talk about how we do something about the problem. So here's one way to do something about the problem. This idea of counterbalancing or Latin squares, that's one common design for this. So if we have a factor with 2 levels, right, say A and B, participants are divided into 2 groups. So like two types of keyboards here, say. Yeah? Participants are divided into 2 groups. Half of the participants go through the conditions in the AB order. The other half go through the conditions in the opposite order, BA. Right? So whatever learning effects there are will disappear or will average out between the 2 groups because they will be in opposite directions. That makes sense? So this is called a 2 by 2 Latin square. So this particular design, right? So you're essentially flipping the order in which they do the conditions. Okay, so now you could do this with more than 2 by 2, obviously. So here is what these look like. You can look these up. So that 3 by 3 Latin squares and 4 by 4, etc. So you can see, in the 3 by 3, for example, ABC, and then you shift, goes BC and then A, and then you shift again, right? CAB, right? So is it obvious that the advantage of this design is that you don't need to have a fully factorial design? right? Because to test, if I do a fully factorial design with 3 conditions, I need 2 to the power 3 conditions or whatever sequences, right? Here I just need exactly 3 sequences. So this grows linearly with the number of conditions. Okay, so look back at this. Okay. 2 conditions. So 2 levels for each of these factors, right? A1, A2, B1, B2. 2 levels for each of these factors. 4 conditions, right? In the Latin square design, we had how many? 2, right? If I have 3 levels, or rather, sort of 3 factors with 2 levels each, rather. ABC with 2 levels each. I would need 8 of these. Is that right? Or 6 of these? 8? And I can get away with just 3 in the Latin square, right? So it's a much more efficient way of scaling, right? I cannot do this fully factorial design, right? It's just too many I need too many participants for that, which is why the Latin square is a solution to that problem, as well as a solution to the order effect problem, right? Because now I don't just do these things in the same order, right? I do them in different order across the different sequences, conditions. Okay. So, in the first one, I do A first and then B. In the second one, I do B first and then A, for example, eventually. Okay. So this addresses order effects and addresses the problem with fully factorial designs of just not being able to scale up, which is why everybody uses Latin squares for designing their experiments. Okay. Okay, so let's look at the concrete example here for a minute. So let's say I have three editing methods that I'm looking to test, A, B, and C. And I hypothesize that they will impact the time required to do common text editing tasks. Method A is I use the arrow keys on my keyboard to get to the point in the document where I need to edit, and then I hit backspace or delete to edit, and then I type whatever the new text is. Okay, so that's method A. Method B is I use find replace or search replace with the dialogue thing, right? To replace some word with another. Method C is I use my mouse and I point and double click on the word that I'm looking to replace, and then I type its replacement. Right? So these are 3 methods to navigate to a word and replace it in a text document. Okay. So I have, say, 12 participants that I recruit for this experiment. And because I've taken this class, I worry about experiment design, and I want to counterbalance for learning effects. So I divide them in 3 groups, and I administer the tasks according to this Latin square design, which is the one you see there on the slide. Okay. So the first subgroup, which is 4 participants, does the task 5 times. So I repeat the task to get a bit more statistical power here and reduce noise in these different orders. Second subgroup uses the second sequence, and the third subgroup uses the third sequence. They do 5 tasks each in each of these conditions, maybe 5 different documents, 5 words to replace, something like that. Okay. So far, so good? Yep. Okay, so that's the setup. Okay. So here's what I get back, right? This is the data I collect from running this experiment, right? So you see the 12 participants there. Those are the 12 rows. The test conditions. So I've grouped the time it took them to find and replace these words in each of the three test conditions, A, B, and C. Those are the three methods of like using the arrow keys, using search replace, and using the mouse. And then you can see also how the participants were assigned to these different sequences. You know, group one, the first four participants did ABC, group two, the next four did BCA, group three did CAB. Okay, so that's just the data tabulated from the experiment. These are the times it took them to do the average times it took them to do the 5 tasks in that particular condition. Okay. All right. So here's some interesting things. If I look at the A method of editing, right? So this was using the arrow keys, right? The people that did A first are about a second slower on average than the people that did A second after having done C. You see this? Right? So these people did A after having done C, and they're about a second faster on average than the other people that started by doing A. Right? So this would show you learning effects, right? On average, they can shave off about a second on the task if they're more familiar with the experiment to begin with, which they get out of doing a different task in a different condition first. Okay? So learning. You also see fatigue, or nothing at all if there's a Zoom thing overlaid. So here, the people that did A at the end of the experiment, after doing the other two, are about a second slower still than the first group. Okay, so this could be indicative of fatigue. Right? They just got tired. Right? The experiment maybe ran too long. They got tired. Marco.
So in this case, it would be, you would see something like the group that did A first, let's say they're at 15 seconds on average. The group that did A second, they're on 14 seconds on average.
Yep.
Yeah, and then the last one that did A last, they did 16 seconds on average. So you see learning and then high, like fatigue set in really hard, yes.
Not among the same groups, right? Because they didn't do, it's different groups, that subgroups that did
But then if you're saying that the subgroups do matter, then how can you claim that this is fatigue?
yeah, so it's fatigue in the sense that you expect that right. So it is fatigue because the groups here are expected to be indistinguishable in their ability to do A, except for when they do A. Right? The only difference here is when they did A, but otherwise, because of random assignment or something, they should be indistinguishable on average in their ability to do A. Right? So I'm showing you that if you do A at the beginning of the experiment, you're faster than if you do A at the end of the experiment. And that could be indicative of fatigue, because otherwise, why else would it be?
Yeah.
It could also be, sort of, I guess, or learning bad habits from the other things, right? So maybe not fatigue, but anti-learning or something. It would be something like that as well. So I'm not sure if it's only fatigue, but it could be fatigue. Okay, how are we doing? Still with me? Okay. So, but if I look at the overall time it took the three subgroups to do the experiment, I can see no difference. Right, so that's great. Right, that's what you'd expect, right? Because the three subgroups should be indistinguishable overall, right, across the whole experiment. And so that means counterbalancing actually worked. The Latin square design was sort of a good design here. Right? It removed these, order effects. And finally, if I actually now compare the three editing methods, right? I see that maybe the third one is the most efficient. The third one was, I don't know, using your mouse to navigate to whatever the word is, selecting it and then typing a replacement. Right? So, note the error bars here are very wide. So maybe the sample size is not large enough to actually, draw a statistically significant conclusion. That's not the point of the illustration. But you can see how, imagine you had larger groups, etc. This is trending in that direction towards that conclusion. Right? So you can still detect differences between these methods, right? But you were able to remove these order effects, learning and fatigue, through counterbalancing, which is what this Latin square design gave you. Okay, that's a great thing. So hopefully you will remember this idea of counterbalancing as important, and the Latin square design as one solution for this. Maybe the most common, I don't know. I don't do a lot of experiments. I don't know if it's the most common. It's certainly very common. Okay. Right, so now one more thing here that you could complain about. Let's see if you catch it. What's wrong with, let's take the third one as an example. What's wrong with this still?
Can you guess here, which I have a question about like C never happens after A, when do you care about that?
Yes, we do care about this, right? So remember, we had to cut corners somewhere, right? If we hadn't cut any corners, we would have had a fully factorial design, right? We had to cut corners because we cannot afford a fully factorial design. So this is one of the things we're losing in the process of cutting corners. With something like this, conditions precede and follow each other an unequal number of times. I think that's fundamentally what you're saying. Right, so the A-B sequence here is more common than the B-A sequence. Right, and that's true of others as well. So if there is a sequence effect, right, it's not fully compensated by this design. Right, so you would need to run a fully factorial design or something like that to do that, to test that. Right, this by itself. So this is one to known limitation. It's maybe a small price to pay for otherwise a great design. But just be aware of this. Okay. Okay. So now let's see if I can squeeze another interesting thing in. We have two scanning keyboards. The first one is this classical keyboard. So you sort of, you scan through the different letters, kind of like what happens on a TV when you have to type on, you're super annoying, your like username and password into some streaming account by scanning through that virtual keyboard on the TV screen, right? As opposed to, I don't know, using your phone to scan a QR code or something. So that's kind of the idea there, super annoying. The second version, the one on the bottom, adds an LLM to this that predicts the next word, right? The most likely word. So you don't have to type the whole way. It predicts as you're typing and it suggests, the most likely words, and you can sort of take shortcuts that way. Okay. So you're designing an experiment to test the effectiveness of this new machine learning based predictive keyboard or scanning keyboard. You have done counterbalancing because you have taken this class and you know that's a good thing. Okay, so yellow here maps to yellow there. So the first half of your participants are doing the simple keyword first, and then they graduate to this predictive keyboard. The other half are doing this in the other order. Okay, groups 1 and 2, they do this experiment in the different orders. Okay, yes, with me? Okay, very good. All right, so now if you look at the results, the ones I just mentioned, so these are the times it took them to do whatever tasks. If you look at the results, the entry speed, no difference between the two keyboards here, say. The predictive one takes about as long as the traditional one. Okay. You can see maybe strong learning effects, right? The first half is a lot faster than the second half. Sorry, slower than the second half. So this is characters per minute. That's a typing speed measure. So the second one is faster. They type more characters per minute in the second half of the experiment. So everybody learns from, typing something in the first half, and they type faster in the second half. And here's where it gets interesting. There's this asymmetric skill transfer, seemingly, between the two groups. Meaning, it seems like the sequence really made a difference on how much learning there was. Okay? So, both groups improved, even at comparable rates. So group 1, the fancy keyboard with machine learning, word prediction is the red square. Okay. Thing, right? So one of the groups started with the plain. So group 1 started with the plain keyboard, and then graduated to the one with word prediction. Group 2 started with the predictive keyboard, and then went back to the one without word prediction. Okay, these were the two groups. Both of them improved between the first half and the second half of the experiment, because the speed at which they're typing went up in both cases. Okay. But turns out it's harder to start with the more complex keyboard, the one with word prediction, right? The people that started with the simpler keyboard type faster per minute. Okay. But it's more efficient ultimately to use the predictive keyboard than the traditional one. So this is that asymmetric skill transfer that I was telling you about. It seems it is useful to learn the traditional keyboard first and then graduate to AI. Just like maybe it's useful to learn, I don't know, computer science or software engineering or whatever, how to program first, and then graduate to using Claude Code. Then the other way around. So that's kind of the analogy here. Okay. Right, so this is maybe a good time to end. I want to leave you with this idea of asymmetric skill transfer, and we'll pick up on this next time. So this means the sequence mattered here, right? The counterbalancing didn't quite fix everything, right? That's it. Thank you. I'll see you next time.